All right, let's jump right in. Today, we're going to talk about the secret sauce that runs pretty much everything you use, from your phone's apps to massive websites. It's called Object-Oriented Programming, or OOP. Sounds kind of technical, right? Don't worry, we're going to break it down and see how it turns total code chaos into something clean and powerful.
So just think about this for a second. A site like Amazon has millions, literally millions of products. Every single one has a name, a price, a description, reviews. I mean, the list goes on. How on earth do you manage all that data without the entire system just imploding? That right there, that's the exact problem OOP was born to solve.
You know, if you're writing a tiny little script, sure, you can just write one long list of commands. It works. But try doing that for a massive online store. It would be a complete nightmare. You'd be copying and pasting code everywhere, and if you needed to change one little thing, you'd risk breaking everything else. It's fragile, it's messy, and it just doesn't work for big projects.
Let's just call it what it is. If you've got 50 products and you find yourself writing the same block of code 50 times, that's just bad programming. It's a waste of time and it's asking for trouble. There has to be a smarter way, a more efficient way to do things. And that brings us to the first big idea in OOP.
So, what's the big secret? Well, the core idea is to separate the design of something from the actual thing itself. In the world of OOP, we call this classes and objects. The easiest way to think about it is like this. First, you create a blueprint, and then you use that blueprint to build as many real things as you want.
And this is a really crucial distinction. The class is just the blueprint. It's the design for a car on a computer screen at a factory. It doesn't exist in the real world, and in programming terms, it doesn't take up any memory. But the actual cars that roll off the assembly line, those are the objects. Each one is a real, tangible thing built from that one blueprint, and each one takes up its own space in your computer's memory.
Now check this out. This is what that blueprint can look like in actual code. Here, we're defining a class called product. And all we're saying is that anything we create from this blueprint must have a name, a price, and a description. That's it. This one little template sets the rules for every single product we're ever going to create.
And this is where the magic happens. Once that blueprint exists, we can stamp out as many individual, unique products as we need. Product 1, Product 2, Product 3. You could make millions of them. Each one is its own separate thing, but they were all created instantly from that single piece of code. No more copying and pasting. That is incredibly powerful.
Okay, so this is great. We're making all these objects from our blueprint, but this creates a new problem, doesn't it? How do we keep the data inside those objects safe? What's to stop someone or some other part of the code from accidentally setting the price of a laptop to, I don't know, -$50?
So if all the data inside our object is just out there in the open, what we call public, then any part of the program can just reach in and change it. And this right here is a perfect example of why that's so dangerous. You could easily set the price to a nonsense value like -50. That's a bug just waiting to happen, and it leads to corrupted, unreliable data. We need a better way. And the solution has a kind of fancy name, Encapsulation. But don't let the name intimidate you. The idea is actually super simple. Think of it like a vitamin capsule. You're taking all the important data, bundling it together with the specific functions that are allowed to change that data, and sealing it all up in a protective shell. It's all about hiding your data and controlling access to it. And here's what that looks like in practice. See how the price is now marked as private? That means it's locked away, hidden from the outside world. The only way to change it is by going through that public function, setPrice. That function acts like a bouncer at a club. It's our gatekeeper. It checks the new value first, and only if the price is 0 or more does it actually let the change happen. Problem solved. No more bad data.
All right, let's keep building on this. We've got our basic product class, and it's secure. But what happens when we need to create a more specific type of product? Say an electronic product. It's still a product, but it's got some extra stuff too.
So think about it. An electronic product definitely needs a name and a price, just like every other product. But it also needs something unique, like a warranty period. Now, the first instinct might be to just copy the entire product class, paste it, rename it, and add one new line for the warranty. But we already know where that leads, right? Duplicated code is a mess. Instead, OOP gives us this beautiful solution called inheritance. And it works exactly like a family tree. We start with our main product class as the parent. Then we create a new child class, electronic product, and we tell it to inherit everything from its parent, so it automatically gets the name and price. Then all we have to do is extend it by adding the new stuff it needs, like that warranty.
And that is the absolute key takeaway for inheritance. At its heart, it's all about code reusability. The child class gets all the powers and properties of the parent class for free, without you having to write a single extra line of code for it. You just build on top of what's already there. It's efficient and it's smart.
So these concepts we've been walking through, the secure capsule with encapsulation, the family tree of inheritance, they aren't just random tricks. They're actually part of a much bigger toolkit. They are two of what are famously known as the 4 pillars of object-oriented programming. These are the fundamental ideas that make modern software possible.
And here they are all together. We've talked about encapsulation, which is all about protecting data, and inheritance, which is for reusing code. Then there's abstraction. The best analogy for that is the dashboard of your car. It hides all the insane complexity of the engine and just gives you a steering wheel and pedals. And finally, polymorphism, which is just a fancy way of saying that you can treat different objects in a similar way. You can have one drive command that works for a car, a truck, or a bus. These 4 ideas are the foundation.
And that brings us right back to where we started. By using these 4 pillars, we can move away from that messy, chaotic, impossible-to-manage list of instructions. We get to build a world of structured clarity, a world where we can create reliable, reusable, and secure little building blocks that we can then piece together to make something incredibly complex and powerful.
So what we've really done is unpack the toolbox that's used to build the software that literally runs our world. These aren't just theories, they are the practical tools of the trade. And now that you understand the thinking behind it all, the question isn't just about what you can build. The real question is, what amazing problem are you going to solve first?